This last session of the day. So the session is on modeling, models. And the first talk will be given by Ocan Sankur from Inria and will be on the verification of generic VHDL systems. Okay, so please.
This is joint work with Benoît and Florian Faissole from Mitsubishi Electric around Central Europe. We're interested in hardware verification for critical components. We use the Rocq proof assistant to prove some hardware components. So typically, when you do this, you first I don't have a pointer. Okay, you first develop your hardware. We use VHDL. You could use something else. We use VHDL. You do some testing, and eventually you're satisfied with your design, and then you want to write proofs. Write properties and proofs in Rocq, but of course in the middle you need to translate to Rocq because Rocq cannot read VHDL, so you need some equivalent design in Rocq. This also means not only to translate the design but also have some semantics of VHDL. So I'm interested in this step. Of course, this is not a new topic. So in the literature, people have been verifying hardware using proof assistants. So I would say there are mainly two approaches. The first one, the most satisfying academically and most elegant way, is to design the hardware within the proof assistant, that is within this environment, which means you have a language, you have some formalization properties and so on. And maybe you even have some translation to RTL or even netlist synthesis, which is also proven in your framework. So that's very elegant, but this also assumes that you have hardware developers who are willing to use your proof assistants or your new language. This also means that if you have existing hardware designs, you still need to translate them. And so in those cases, for instance, we had existing design, and so in that case you do the second step and the second way, which is either manual or automatic translation, which then you try to justify. So in our setting, yeah, indeed, our target are existing pipeline designs in VHDL, very low VHDL, and we had hardware developers who will not use your favorite proof assistant. So they have their own tools, they know what they're doing, and they will not use something else. So this was given, and our goal was to actually find a trade-off to use the formal methods to have strong guarantees, but also have something feasible within reasonable budget and time. So I want to summarize the steps, a few steps. This is also the overview of the talk, an overview of our work. So you first focus on combinational designs. So the combinational circuit is a circuit that has no states. So there are no registers and no flip-flops. So it's really you give inputs, and you get within the same clock cycle, you get outputs. So this is, of course, much simpler. This is a fragment of VHDL. So we developed a translator from some combinational fragment of VHDL to Rocq. So this comes with some formalization of the semantics. But actually, this translator makes several assumptions to simplify our work. We make several assumptions, which I will detail. Our translator is not only a translator, it also checks several properties of the design to make sure that indeed we can translate under assumptions. So I will focus on this just in a minute. And just to complete the picture, so then we deal with pipeline designs by reduction to combinational circuits. So we use hardware equivalence checking algorithms, which is basically model checking, to establish. So I just want to give the big picture, and then I will go into detail of several steps. On the left, so we are given a pipeline design. So I will explain how we obtain a combinational design, which is equivalent in some sense, and we use hardware equivalence checking algorithms to check that this equivalence holds. And once this is done, now we use our translator to go to Rocq, write properties, prove, and so on. So this is the whole picture. Yeah, so the whole thing is our work, but I would say I will focus mainly on these steps, which are maybe our contributions. Okay, so here's what I mean by translating VHDL to Rocq. So in VHDL, you can write generic circuits, generic designs. Generic means So here's an entity in VHDL. So an entity is like a signature in VHDL. So you specify E and P, which are just integer parameters, the generics. And given such values for E and P, the entity specifies that this is a circuit with input vectors x and y of size E plus P, and output vector z and some flags. So this is a floating point adder. And so this means that if you give values to E and P, for instance 8 and 24, then you can synthesize a circuit that will look like this. On the left you have the input vectors x and y, on the right you have the outputs, and so on. So this means that for each instantiation of the generics, you get a different circuit. All right, so, and by our assumption that all designs are combinational, this also means that the circuits are functional in terms of, they define functions that is given values for x and y. You will always get the same value z, regardless of the paths, because there are no states. So this is very good because we use Rocq, and we have a functional language, so we're going to map entities to functions. So when we translate from VHDL to Rocq, we want a generic translation. So here's what I mean by this. So if the signature of the translated function should look like this, so if you given the float adder entity, we want a float adder function which takes as arguments values for generics, E and P, and then input vectors. And it will output, so this tuple, which is the type of the output signals. So this makes sense. I mean, generics must be arguments of the Rocq function because, of course, if you given a floating point unit, floating point operations as an example, of course, you can instantiate for single precision, double precision, custom precision. And we're going to prove properties of such designs. And we want one single proof of correctness for a generic FPU design. So we do not want to maintain several proofs for each possible instantiation. Yeah, this is not elegant and this doesn't make sense. All right. So yeah, now I will show how we translate combinational circuits to Rocq. And then I will show you why this is not entirely obvious due to, mainly due to generics. But let me start with something even simpler. So VHDL and programming languages are very different in nature. So VHDL basically describes circuits which, if you execute them, compute something. And they do so, I mean, the physical circuit computes in parallel. So you're basically defining gates which will compute in parallel. And of course, Rocq's language is sequential and functional. So on the left, you have a really simple circuit with internal signals x and y. These are Boolean signals. And x gets the value of not y, and y gets the value I, which is an input. So in VHDL, the order of these statements doesn't matter because it's in parallel. But the semantics, I mean, if you read the manual, the VHDL reference, they say to simulate such a circuit, you can evaluate in any order. However, you need to start again until stabilization. I mean, I simplify it a little bit. But of course, we know that in a combinational circuit without loops, you can actually go ahead and directly define the final value of each signal. So here, for instance, you first define y, and then define x, because x depends on y. So there's some topological ordering which you can compute it. So this is not difficult. This means that you need to analyze the design and compute this order. So this is very simple, but it gets a little bit less simple because we have generic designs. So as I said, generic designs describe an infinite number of circuits theoretically, and we only want to translate once. We want one translation that should match the circuit. This means that there should be one common topological order for all those circuits. And is this possible? So I want to show one case where there's no topological order, no common topological order. So you can write things like this in VHDL. So you have here T1, T2, two internal signals. And you can have, so T1, so the first line, the assignment to T1, that's a conditional assignment. So T1 gets the value of A, which is an input, if P is less than or equal to Q. Otherwise, it gets the value of T2. And T2 is quite similar, so T2 gets A. In the other case, Otherwise, it gets the value of T1. So both signals depend on each other, but under different conditions. So there are no loops. There's no loop. But clearly, T2 must be defined before T1 if P is less than or equal to Q, but otherwise it must be defined later, afterwards. So this means if you want, well, you could of course translate to some sequential language, but if you want a really simple let expressions, if you want a simple translation, well, there's no translation. Because there are two translations which you should use in two different conditions on P and Q. So how? Our tool will check this, will detect such situations. So of course, here's how we do. So I've been talking about topological ordering, which means we define a graph, imagine a graph. So we define the edge between statement 1 to statement 2. If statement 1 assigns a signal that is read in statement 2. So below this edge, because y is assigned on the first line, but y is used on the second line. So these edges just show the order of evaluation you should have. But of course, this is not the whole story, because there are the generics. So the condition is that if ST1 assigns a signal that is read in ST2 under some valuation of the generics and loop indices, then you put an edge. So this means with this definition, there's a cycle on the first example, because for some values of the generics P and Q, T2 should come before T1, and for some other value of the generics, the other way around. So you get a cycle. Once you have the cycle, of course, you can detect that there is no topological ordering of the statements. Okay, and there's another example here, so more complex. Below you have a loop, which contains a conditional, and inside there's an assignment to ui. So u is a vector, ui is assigned something. And if you look closely, so ui is assigned between I from 0 up to 9, but also depends on n. And you can see that u0 is assigned here and read on the first statement. So basically, that's why there's an edge. And well, formally, for for some valuation of the generics, and loop indices for n equals to 1 and I equals to 0, indeed, u0 is assigned in the loop, and it is also used on the first line. So that's why there's an edge. So that's how we reason. And of course, it is possible to decide each edge. You can write a SMT query. That's what we do, guessing the values of the generics and loop indices and dealing with all those conditionals and loop invariants and so on. So I won't show the query, but this is possible. In our case, most constraints were linear. We had a few quadratic constraints, but these were, in most cases, rather small queries, so they were quite fast. Right, so now I want to mention another issue we have in VHDL. So something we dealt with during translation. So in VHDL, I guess also in Verilog, people use, signals have Boolean values, but actually these are not just 1 and 0. You have 9 values for each signal. This is the standard library. This is how you do the things in hardware. So I will not comment on everything, but just to give an example. So this value x, for instance, your signal becomes x if you have 2 statements writing to the same signal. So if you have multiple drivers to a signal, you'll get x. So, and you certainly don't want to deal with 9 possible values when writing proofs. So imagine a binary operator, 9 times 9. So you don't want to do this. Fortunately, we know by the semantics of VHDL that in a combinational design, if all inputs are 0 or 1, and if each signal is assigned exactly once, then all outputs and internal signals are guaranteed to be 0 or 1. So you don't, and then these other values will not appear. So this is a theorem, handwritten theorem by the semantics of VHDL. So this is what we will use to simplify the translation. So we actually check that each signal is indeed assigned exactly once for all generic valuations. That's, again, a bit less obvious than the case with our generics. we need to check that, yeah, that there are no multiple assignments, and there's also no missing assignments for all generic valuations. So if this check passes, then indeed our translation our translation will map STD logic signals to Boolean, just Boolean 0, 1 in Rocq, which is then much simpler. Yeah. So what do I mean by multiple assignments to signals? So here in this example, you have a vector v of size n, so generic n, and this is a simple simple definition of the values of the vector v. So v0 is assigned first, and this loop assigns values between indices 1 to n-2, and then the last value is assigned at the end. So this looks okay, but of course this depends on n. So if n is equal to 1, then you get a double assignment. So if n is equal to 1, yeah, then the loop doesn't get generated, it disappears, and you have v0 equals to 1, v0 equals to 0 at the last line. You actually get x. So this is typically a design which we reject. So if you want to translate to Rocq, then you need to work on it again and give us a better design. Yes, again, I'm not going to show you the query, but again, we write this SMT query to check this. So basically, we go over all pairs of statements writing to the same vectors and check if for some values of the generics and for some loop index values, is it possible that they write to the same, exactly the same signal. Okay, and once such checks are done, I just want to show just a few examples what the translation looks like. So we have already seen this. So such simple statements just become let expressions, giving the last final value, stabilized value. Because all entities are functional, when you have component instantiation. So component instantiation means given another entity, you can of course instantiate it, which becomes a subcircuit in your circuit. And so subcircuits, subcomponents just become function calls because we know that the other file, the other entity is also a function. So then the translated function just looks like this. The full adder function just calling the half adder function. We have our own little library for vectors. For instance, a vector assignment to value v of 0 looks like this. So I just showed the syntax, but we have an operator that defines a new vector out of existing v by just modifying the 0th element. So the expression on the right defines a new vector, and then we just, with the let expression, we just overwrite the name v. So if you have several assignments, v0, then v1, and so you'll have let v something, and let v something, and let v something. And then for generic loops, of course, this in the functional languages, you don't have for loops, but you have iterators. So this is like something like a fold left operation. So the n.iter will iterate the given function n times, starting from you give the initial value you give to this function is the current values of signals. And the function will just emulate the one iteration. It will just compute next values and return next values. Okay, so this is just how you would encode just a for loop in a functional language. Right. So my point here is that I think the translation is quite simple. I think it's as simple as it could be, and this is important because then. We write Rocq proofs, and of course, if your translation is very simple, then this is much less effort. So the overall tool looks like this. We have VHDL. So we rely on several open source tools like GHDL for parsing. And so we let GHDL build the syntax tree, and we just analyze, we do our checks on the syntax tree. So I mentioned partly the unique assignment check. We do other analyses like we check array bounds. Again, array bounds can be violated for some generic valuations, but not for others. So this is again the SMT. And we also check for integer ranges for integer signals. and overflows and so on. And we can also check dead code. So there are many analyses that are done, mostly with the same ideas I presented. So if all those checks pass, then we try to compute the topological order. And then we can translate to Rocq. So basically the tool can be also used as a linter verifier or whatever for VHDL. So we have a nice plugin that will tell you the errors, and that will also give you, thanks to this empty solver Z3, for which values of the generics you have an issue, whether you have, like it points to two lines that try to assign the same signal and so on. So it will help you develop VHDL that can be then verified, that can be translated. And then eventually you translate to Rocq. All right, so that was for combinational circuits. Now I want to show how we deal with pipeline designs. So this is, again, this was the big picture. So I will talk about the left part here. So what is a pipeline circuit? So let's start with a combinational circuit that looks like this with a few gates. Again, combinational means that given inputs A and B within one clock cycle, you have stabilization, and at the end you can read the output. And so you could pipeline such a circuit by adding registers, so shown in blue squares. So you could put registers, so a register will just delay the computation for one clock cycle. So adding such registers means that you're doing the computation like shown in here in 3 steps. So at the first step, so the given inputs A and B, so all the gates will stabilize. I mean, for this part will be computed, and then we will wait for the next clock cycle. And the next clock cycle, all these values are correct. And at the 3rd clock cycle, you can read the output. So this is just about delaying the computation. And we restrict for now to simple pipelines. What I mean by simple pipelines is that between each input and output, you have the same depth of registers. So that is the same pipeline stages. This, in practice, this means that we're interested in components of a bigger design where you have the same pipeline depth. Okay, our problem was the other way around. So we start with pipeline designs, and now we can only analyze combinational circuits in Rocq. So what we do is that we start with the pipeline design, and we remove the registers. We can just syntactically remove and short circuit the registers. You get something combinational, which then you can prove. You translate to Rocq and prove. So of course, yeah, this is easy to do, but then the question remains, so these 2 circuits are supposed to be equivalent. Are they really equivalent? And you could also do something in between. So what we do, we do remove the registers, but then you can also change a little bit, a few things. For instance, if you have unsupported VHDL constructs, or if you know that some small components will be proven easily if you rewrite it, you can also change stuff. So this is more or less what we do. So basically, we have some alternative combinational circuits done manually, and we think that this is equivalent to the pipeline design. So what we do, so the picture looks like this. We have pipeline design. We remove registers. Maybe we tweak a little bit. You get a combinational design. And so we want these to be equivalent in the following sense. So for all inputs, for all primary inputs, the pipeline circuit must output after k clock cycles what the combinational circuit outputs in one shot. So this is the intuition, because the pipeline circuit just delays the computation. This is what you want. And you can check this with, we don't check this with proof assistance, we check this with model checking or hardware equivalence checking algorithms. So just to show you the idea, we synthesize a netlist from the pipeline design. And then we just disconnect the registers, and we get a combinational circuit netlist that looks like this. You have the inputs and outputs, and then because you disconnected the registers, now the current value of the register now is an input. So if you give the input as an input the current values, then you can read the outputs and you can read the next state values of the register. So this is a really simple syntactic operation. Once you do that, you can then make several copies, connecting the next state values to the current state value. So this is really the unrolling and bounded model checking. It's the same thing. And then you can compare this with the combinational design. Now you have two combinational circuits, and there's a literature over 30 years or maybe more comparing combinational designs in hardware verification literature. So that's what we use. So to show the final picture and the tools, so from the pipeline design, we use tools like ABC, IOSIS and ABC, open source tools, to synthesize a netlist, which we then unroll. And the combinational design, we also synthesize it to a netlist and then check with ABC or also IOSIS and other tools. We check their equivalence. And this is how we establish, this is satisfactory for us. So we think that then the pipeline design is equivalent to the combinational design. And then with our translator, we go to Rocq and write proofs and so on. And yeah. Okay, so this, should I stop or no? Okay, this is the full picture. I mentioned a few things, but as an application, one of the applications is a generic floating point unit verification. And the details of the case study will appear maybe hopefully later. So this is not in the paper. Okay, and I'll let you read. I don't remember what I wrote.
Thank you.
So you talk about the verification of pipeline designs, and so what's the main difference between like general sequential circuits with one clock domain and the pipeline design? Because when you are doing the unfolding, you can pretty much do the same thing for sequential circuits, no?
You could do for sequential circuits. That's how you verify sequential circuits. But what we exploit here is that once you unfold for a finite number of steps, then you really get something equivalent. That is, although a sequential circuit, it's like computing something with registers, you can unfold it, unroll it, but it will not be, you'll get a combinational circuit, but it will just represent the computation over bounded number of steps, right? Mm-hmm. So you might not get something completely equivalent.
Okay, so you count that like you have a finite number of steps, and then you get the thing which is equivalent to the non-pipelined. Right?
Yeah.
Okay.
What kind of top-level specification do you verify against?
Could you say again?
What kind of property are you proving at the top level in Rocq?
Oh, in the FPU or?
Yeah, or in the FPU case or in the other.
The goal would be to prove, so given we had some open source design, FPU, and the goal is to show that each operation conforms to the IEEE 754 standard, which is, we have some formalization of these properties, and we show that these match.
Yeah.
So
you verify at the block level, so you have a floating point adding block, and you verify that the input-output match.
Yes.
Yeah. Okay.
Yeah. Exactly.
Question, please.
Thank you for the talk. You were restricting like the different possible values for the different circuit gates to only be 0 or 1. Are there any input circuits that are of interest where that actually isn't possible? Where there might be an X value in, but you actually still, that is, as technically speaking, still a valid circuit you wanted to prove?
Well, these values are used, right? But I think that they're used in simulation, and in synthesis, I don't exactly know what they become. So in multiple drivers, so this depends on the options you select, I think, during synthesis. Yes, if you want your specification to talk about these, I guess yes, but I'm not sure exactly what Z or X or undefined or this, what did they become their synthesis? Because eventually, I didn't talk about synthesis, but eventually you want to synthesize to circuit or to FPGA, and then I don't know how to link what would happen, what does X mean in the FPGA? So I don't know that. So
Thank you.
Last short question.
Hi, thanks for the talk. So you explained how to prove the equivalence of pipeline component, but do you need to, like by unrolling the circuits multiple times, do you have to do that for every output, or do you have a restriction that all outputs have the same depth?
yeah, they have the same depth. And we, my hypothesis for now, I don't know, remember. Yeah, whatever the inputs you give, you're going to read the value after k steps, k clock cycles, for all output bits, right? So the depth is uniform, whatever the operation you're doing on the circuit.
Okay.
So really, after k steps, you'll get your value. So yeah, we just unroll once, and that's the.
Okay, thanks.
Okay, so let's thanks the speaker.